This lecture on the history of the atom is going to be split in half into two separate lectures. In the first one, I'm just going to cover the experiments by the 5 scientists or groups of scientists that are most important for our quiz in illustrating how the atom has changed over time. In the second lecture, I'll entitle that 3.2a or something like that. Then I will go over the timeline with the rest of the scientists just for interest. The first scientist that we want to talk about is Democritus. Democritus was one of the ancient Greeks in about 400 BC. This is around the time of Plato and Aristotle. And he was doing experiments on breaking materials into the smallest pieces possible. And he proposed that every material or every part of matter in the universe is made of teeny tiny solid particles. And he named these tiny particles atomos, which is obviously, you can see where the word atom comes from. Atomos means indivisible, which means that it does not have any smaller particles, and so the atom is the smallest part of the universe. The view of atomos being the smallest particle of the universe was held almost all the way up until the late 1800s, 1900, although there were many other elements that were discovered and many other bits about chemistry were discovered. It was still believed that the atom was a solid particle. This is until Thomson, J.J. Thomson of England, he started doing experiments on electricity with atoms, and he found that there is a small part that comes out of the atom, and that small part was attracted to one side of a magnet and repelled by the other. And this gave him a lot of information, which we'll discuss further in the lecture. And that led him to coming up with what's called the plum pudding model of the atom. Shortly after Thomson's work, Ernest Rutherford, also of England, was working with radioactive particles in the atom, and he found that that there was something solid in the atom, because he found that radioactive particles most of them passed straight through, as expected for an atom that is mostly a cloud-like type of piece of matter that has small particles inside of it. However, there were some alpha particles that were deflected, which showed that there must be a solid object. And he named that small particle the nucleus, after the idea of a cell having a nucleus in the cell. And so his atom was called the nuclear atom, is how he named his model. Around this same time, Niels Bohr, who was actually one of Rutherford's undergraduate or graduate students, he was working with exciting electrons as well. And he was working with hydrogen electrons and found that hydrogen electrons, when excited, will emit 4 different wavelengths of light. And so he proposed that the atom is organized sort of like the planets in orbit around the nucleus, where that the electrons are in certain energy levels or orbits which allow them to emit this certain pattern of wavelengths. Again, this same year was J.J. Thomson, and he had another discovery which was very important for the discovery and model of the atom. He was the first person to observe evidence of there being isotopes. Finally, the last scientists we want to talk about in the discovery of the atom here are Werner Heisenberg and Erwin Schrödinger. Not much longer after the discovery of the isotopes and Bohr's idea that the atom looks sort of is organized sort of like the planets around the sun, Heisenberg and Schrödinger disproved this hypothesis of Bohr's by testing the excitability and the wavelengths that are given off by other elements. And they found that, or they agreed with Bohr, that hydrogen has sort of a circular pattern in terms of how its electrons move, but this doesn't fit for the other elements. And they were able to use mathematics based on physics, and they were able to sort of make a graph of where the electron is likely to be found and not likely to be found. And it was definitely not in the same shape of the elliptical orbits that Bohr had hypothesized. And they came up with what's called the quantum mechanical model of the atom. And we'll talk about that further on. So let's look at each of these atomic models in a little bit greater detail. The first one was, as we had said, the model proposed by Democritus. About 1,000 or 2,000 years after Democritus, there is an English scientist by the name of Dalton, and he wrote an essay entitled Atomic Theory, based on the work of Democritus and the other scientists of that time. And in his atomic theory, there are the following main points. They stated at that time they believed that the atom is solid, it does not have any parts or pieces. The atom is electrically neutral, meaning it's not positive or negatively charged. Atoms of the same element are identical to each other, meaning, for example, carbon, all elements of carbon are identical to each other. And then they stated atoms of different elements are different, so carbon atom would be different from a cadmium atom. Atoms cannot be broken apart, created, or changed by a chemical reaction. And atoms can be combined to make compounds in chemical reactions. Most of these tenets of Dalton's atomic theory are still supported by evidence even from today's scientists, except for this one in the middle here, which was disproved by evidence from J.J. Thomson. Thomson, 100 years after the writing of this essay, when he was doing experiments with neon atoms, found that there were two different kinds of atoms, each having a different mass. He knew that they were both neon because they had the same number of protons and the same number of electrons, however they had different masses. And so this was the first evidence that isotopes existed. And this showed that Dalton's principle stating that atoms of the same element are identical is simply not true. They may have the same protons, and they may have the same number of electrons. However, we know now isotopes mean that there can be different atoms with different masses. But let's go back to Thomson's earlier discoveries. So earlier when Thomson was working with the electron, he was working with what's called a cathode ray tube, which is pictured here at the bottom of the screen. And in this cathode ray tube there was gas, and it was trapped in this light bulb looking apparatus. And the gas, when electrocuted, and you can see this is the lines where electricity would go in and the circuit would be completed and go out, there would be a ray that showed up, and it was a ray of light which he proposed was not the atoms themselves, but actual particles that came from those gas atoms. And this ray, as we can see in the picture, is attracted up towards the positive end of a metal plate, which is making an electric field. And it is repelled away from the negative end. And so this shows a number of things about the atom. So from these observations, Thomson concluded that, first of all, atoms are not solid, as Democritus and Dalton had proposed. They must contain subatomic particles, because these are the particles that made that ray of light. These particles must be negatively charged, and this is because they are attracted to the positive side and repelled by the negative side of the magnetic field. This is Coulomb's law, which is, just in short, we say opposites attract. So a positive and a negative charge will attract to each other, which is why magnets work the way they do. However, two positive charges or two negative charges are going to repel each other. Finally, this also was interesting because Thomson also learned that if there are these negative subatomic particles inside the atom, and atoms are overall neutral, there must be some sort of a positively charged part to balance that negative charged part. All this information, he needed to come up with a model, and so he envisioned a plum pudding, which is a bread pudding, much like a muffin. And he imagined that the atom is more like a positively charged sort of cloud of positive charge, much like the bread in the pudding. And there are tiny negatively charged electrons scattered randomly throughout the entire cloud, much like blueberries in a blueberry muffin. And they are what make up the negative charge, and this would account for there being the dual charges, the positive and negative charge, and the fact that the atom is not solid and it must have different pieces in it. So again, this is what's known as the plum pudding model of the atom. The next scientist we discussed is Rutherford. And Rutherford did, as we had mentioned, experiments with alpha particles. So an alpha particle is actually the nucleus of a helium atom. So because it's just the nucleus, it's positively charged, and it's fairly large compared to an electron. So this is a beam of fairly large, positively charged particles that he used and aimed like a laser at this sheet of gold foil. And if the atom is mostly empty space like a cloud, as had been proposed by the plum pudding model, he would expect that all of these alpha particles would pass straight through. However, he found that a fair number of them were scattered and deflected, as were detected by this screen he had set up outside of the gold foil. This led to a number of observations, or a number of conclusions. So Rutherford concluded that the atom must be composed mostly of empty space, as believed by the plum pudding model, and this is because most of the alpha particles pass straight through. However, there must be a solid part, because there was something that was large enough and positive enough to deflect and repel the large alpha particles that were bombarded toward that foil. The solid part, again, it must be positively charged because it repelled the particles. And therefore so he called this the nucleus, because again, like the center of a cell, this is a major component of the atom, like the nucleus is to a cell. So his nuclear atom model looks much like the atom that we sometimes will use today as a depiction of the atom. So he said that in the center there's a nucleus that has a positive charge. Notice it does not have protons or neutrons, because those had not yet been discovered. But there's our positively charged nucleus, and that's surrounded by an electron cloud in which the electrons are not organized in any type or form. Shortly after the discovery, or design, you could say, of the nuclear atom, Bohr, who again was working in the same labs as Rutherford, his experiments led him to the idea of the planetary model, in which the electrons are in fact organized. So again, using this idea of a light bulb filled with gas, much like Thomson's original experiments, Bohr was able to look at the light that came from that bulb, pass it through a prism, and see that there were 4 different colored bands that were emitted. And this shows that there are 4 different amounts of light, or wavelengths of light. And this is what's called an emission spectrum. It's kind of like a pattern. And he observed that this also happens with other elements, and they each have their own distinct pattern. So from this information, he concluded that there must be something in the electron cloud that allows the atom to emit high and low energy of different forms. So he concluded that the electrons are organized in some way, and he called them energy levels because they release different amounts of energy. And he said that the organization of these electrons into energy levels is different for each element, which explains why each element has a distinct pattern. So his planetary model is depicted as electrons organized around the central nucleus, much like planets around the sun. Later experiments and calculations by Heisenberg and Schrödinger were able to refute this hypothesis, because they found that the electrons do not travel predictably, and the data does not work for models other than for the hydrogen atom. So they proposed that instead electrons do not travel in set paths, but they have unique boundaries that they do travel in. And they developed what's called the quantum mechanical model. This model you probably have never seen. As teachers, we do not teach this picture because it is very complicated. And this is a very simple picture. When we start talking about electrons being in energy levels and electron configuration in another month or 2, we'll go into more detail about this. But basically, the quantum mechanical model states that electrons are organized into energy levels of sorts, but their organization is somewhat random into mathematically determined graph patterns that go a certain distance from the nucleus and travel in certain lobes, is what they're referred to. So these are the 4 different models of the atom and the scientists and the discoveries that helped them.